welcome on board. This is Design B Engineering Process, a channel where we give a walkthrough on process engineering operations and design. So for today, we're not going to be diving in as we are already inside. Today's content is going to be very short as it's more of an insight than a content, but we could still call it a content. Extra knowledge. So as you can see, we are kicking off from where we stopped last week on our last content rather, which was the alkaline electrolysis. So we have a comment up here saying, comment from Wolf PY5BD. He says, thank you for this great tutorial. Thank you very much, Wolf. He's also asking about the PEM electrolyzer. Can you make another one for the PEM electrolyzer? And thank you very much for this, Wolf, as you drawed my attention to something very important. The comment section is very open to every single viewer. If you have any problem, you could also put it out there just the way Wolf did, and we will attend to it to the best of our abilities. So, for the PEM electrolyzer, we need to understand that for our previous content, what we had was the alkaline electrolysis, water electrolysis. And for that type of electrolysis, we had to add an electrolyte, which was potassium hydroxide, respect to the previous content. And the reason for that was for us to improve the conductivity of water for electricity. Now, for the PEM electrolysis, using a PEM electrolyzer, it deals with firstly, PEM stands for the Proton Exchange Membrane. So PEM electrolyzer uses a solid polymer electrolyte, often Nafion, that conducts protons, and protons are the positive ions. It conducts the protons from the anode to the cathode. Now, what this simply tells us is that we do not need an electrolyte for PEM electrolysis. All we need is just our water and a PEM electrolyzer. So as such, the configuration, or rather the simulation for a PEM electrolysis, would be slightly different from an alkaline. And for us to make things very easy and short, and at the same time feed our laziness, we're going to work with the previous model for alkaline electrolysis on our previous contents. The only difference is that we do not need an electrolyte, so we're going to disconnect this, but we're not going to delete it. We're going to leave that for a reference, which we will see later on. And we're going to delete this also. We're going to delete every single thing backwards up until the outlet of the electrolyzer. These are the two outlets of the electrolyzer, cathode and anode outlets. Delete this, and this. So everything remains the same up until the point of entering the simulation environment. You know, every single thing about our component list. The only difference is that we are not using potassium hydroxide, but the other components such as water, H2, hydrogen gas, that is, and oxygen gas are still in our component list. The only difference is that there is no potassium hydroxide, even though it's currently on our stream. But let's just assume it's not there. And then for the fluid package, it still remains the same, which is our electrolyte NRTL, and for the reactions, water dissociation, it's still the same. The only difference is that the second reaction for potassium hydroxide, the electrolyte, would not be included. So, as you can see, these are the conditions. 100% water. These are our conditions, stream conditions, and it goes in. And remember, for the alkaline electrolysis, we needed an aftercooler after mixing water and potassium hydroxide, because it produced heat during the reaction. So currently we do not have potassium hydroxide mixing water, and as such there is no heat gain. So we might as well just delete this heater, cooler rather, delete, and plug this into the electrolyzer as our inlet. So much better. Now, the difference, apart from the difference of the simulation where we do not have an electrolyte in our PEM, the configuration also for the electrolyzer is slightly different. For the PEM, we are better off with the electrolyzer model. And as you can see, it's slightly different with respect to the schematics, not like the alkaline. The alkaline, it's a bit different, more simple. But for the PM, as you can see, there's a difference. You use the electrolyzer module. So as you can see, we have two overhead gas liquid separators. That's what I think would be a better reference for them. We have a gas liquid separator, two of them for the for the cathode outlets and the anode outlets. Now, what we expect to go out for our cathode outlet rather, is predominantly hydrogen, because that's a proton going through the cathode. And for the anode, we expect our our negative ion to go out. So at the bottom is for any unreacted water. In this case, we do not need a component splitter to recycle the bottom's unreacted water. This gas liquid separator deals with that action for us naturally. It's an inbuilt configuration. As you can see, it's not on the simulation environment, but then inside the electrolyzer, when you select the electrolyzer module, it gives you this setup. It's already inbuilt, so any unreacted water goes to the bottom, as you can see, and it's recycled and sent back inside the electrolyzer to continue the process. So we have a message at the bottom saying at least 3 purity specs should be available to solve the electrolyzer module. So parameters, as you can see, it's also slightly different. Unlike our alkaline electrolyzer, don't pay much attention to this process that says alkaline water electrolysis, because it's not an it's not a it's more like a custom. Well, I wouldn't really call it a custom build. Aspen Hysys does not give an inbuilt configuration for a PM electrolyzer, so we're just more like conceptually modeling a PM electrolyzer. With the concept, it's there, but yet it's not named. So this is something we cannot change. You do not need to pay much attention to the name. It's more about functionality. So the anode product purity, this is where we need to specify the purity for both the anode and the cathode product purity. This is what this whole message is all about. And as you can see, our power is still there. We have about 21.93 megawatts. And then number of stacks, we have 200 cells, pressure drop 0.5 bar, and Faraday efficiency 93.93%. So let's select our mass as the purity basis, mass flow or mass fraction. So typically for our PM electrolysis, we expect a purity high enough to reach around 99.9%, approximately 100. That's really nice. That's really great. That's the beauty about PM electrolysis. It's better at producing a cleaner hydrogen gas and hydrogen gas majorly. That's the major concentration for electrolysis. A very high purity of hydrogen gas compared to the alkaline water electrolysis. For the alkaline water electrolysis, we were able to produce around greater than 95%. I'm pretty much sure, but it took a lot of stress of recycling, a lot of power inputs. But for the PM electrolysis, it's easily carried out. So for the cathode, we expect our hydrogen gas to be there predominantly, and let's try and set it to 99%. And that leaves us with an oxygen purity inside that stream. Since it's not a component splitter, it does 100% split it. We expect a little trace of oxygen. So let's try 0.01 and a total of 100% in that particular cathode product stream. And for the anode, we're expecting predominantly oxygen gas, so it's going to be 99.9% and 0.01% of hydrogen. So we have a consistency error, as you can see. In general, this means that the simulation is overspecified. And the reason for that is that we do not specify power in our PM electrolyzer. Since we're specifying the purity, the electrolyzer and Aspen Hysys itself tells us the power that we need to achieve that purity that we have set. So we're going to do away with the power, and let's put this back on active, As I as you can see, it's good to go. Aspen Hysys determines a power input of 2.2 megawatts. That's close to what we had earlier, 2.19. So let's look at the purity. With this, we have successfully solved the electrolyzer without having to do anything such as recycling or unnecessary power increase, flow increase, power increase. If you're in our previous content, you get what I mean. So for the hydrogen outlet, the cathode outlet, hydrogen stream, 100% gas, and this is the flow, 559.9 out of 5,000. Then we do have our 99.9, approximately 100% pure hydrogen here, and very, very minute, as good as insignificant water and oxygen present. And for the hydrogen, rather, and for the oxygen, we have 4,441 as our mass flow, and we have a mass fraction of 99.9, approximately 100% oxygen, just like we specified with respect to the purity. So, as you can see, it's very simple to deal with the PEM electrolyzer to produce a purer hydrogen gas compared to using alkaline electrolysis. But the only downside to this is that it's expensive with respect to real life engineering scenarios. It's more expensive than the alkaline because of the proton exchange membrane that you need to have. So the power, it's almost the same with respect to what Aspen Hysys has given us. It might differ in the real life scenario, as this is only a simulation. It can depict the real life behavior to a certain point. So the purities are intact, and this is where our electrolyte stream that we left in. Some of you might be thinking, why go through the stress of recycling that we did for the alkaline electrolysis if you could just use this inbuilt gas liquid separator and it would just do the whole recycling for you? So this is where I need you to take note of something very important. We're going to plug back the electrolyte, even though it's a PEM electrolysis, we're going to plug in the electrolyte, which is potassium hydroxide. And as you can see, it just messes up our electrolyzer. Let's see what we have inside. It says electrolyte module feed must contain only water. And that's similar to what a PEM electrolyzer accepts, only water. I might add to that distilled water free from any impurity or ions or minerals, basically. It's just 100% oxygen and hydrogen present inside, nothing more, nothing less. Ultra pure water. That's what it uses for electrolysis, PEM electrolysis specifically. So that's the reason why we do not use this configuration for alkaline electrolysis. But since it's a PEM electrolysis and it requires only water to carry out electrolysis, you do not need an electrolyte as such. We can do away with this. And you can see for the energy stream that we added for the previous content, we don't need that also for the PEM electrolysis. So with this, we have conceptually modeled a PEM. It's not an inbuilt equipment in the Aspen Hysys model palette. We just have to conceptually try and model it as best as we can. And I think that's the reason why the electrolyzer module is left inside the Aspen Hysys for the PEM, conceptual PEM electrolysis. Well, with this, I think we can get a very good catch on our PEM electrolysis. The only downside to this is that we cannot account for the electrochemical kinetics and physics that occurs inside a real PEM electrolysis. So you might have to use an extra tool beyond Aspen Hysys. For the Aspen Plus, I don't really know for now how it handles the PEM electrolysis. That's something that we might need to look into in the future. But with this, we have covered what we are here for today. So hopefully this was helpful to you, Wolf, and any other viewer who's there. And as always, please make sure to like, subscribe, click on the notification icon, and leave a comment if you found this video helpful or if you have any questions, as we will be doing from now on. Thank you very much. See you soon.